Okay, so 2.1 types of chemical bonds. So enduring understanding, atoms and ions bond due to interactions between them forming molecules. Explain the periodic trend of electronegativity qualitatively through electronic structure of the atoms, Shell model, and Coulomb's law. Determine whether bonds are polar, nonpolar, or ionic based off of the electronegativity differences. Draw dipole moments, assign partial charges to elements in a polar bond. Explain the continuum of bonding and determine the type of bond by examining the properties of the compound. Define metallic bonding and that the valence electrons are delocalized, not associated with any individual atom. All right, chemical bonds. No simple yet complete way to define this, but forces that hold groups of atoms together and make them function as a unit. It's a good description of a chemical bond. Bond will form if the energy of the aggregate is lower than that of the separate atoms. So when we say aggregate is just like just a big word for saying group, the group of the atoms. Okay? So one of the reoccurring themes in chemistry, of course, is all about stability. So, and getting to a lower energy state. Bonds form because it creates stability and it puts them at a lower energy state. So that's the whole purpose of bonding, being able to do that. All right. Key ideas in bonding, ionic bonding. Basically, electrons transfer, you get charged particles, ions. This is a lot of review. You have the metal, which would be the cation, the non-metal, which would be the anion. Cation being positive, they lose electrons. The anion is going to be negative, which means they gain electrons. Now, of course, you do have your group ions too, which are your polyatomic ions. A few of them are cations. A couple of most of them are going to be anions. So as a group, when they gather together, they end up pulling in extra electrons to form the stable anion there. Covalent bonding. Electrons are shared equally by the nuclei, and this is usually a non-metal case, although sometimes you might see it as metalloid bonded to non-metal. Most cases, metalloids bonded to non-metal are going to fall under the covalent category where they're sharing electrons, okay? All right, now, these are the two ends of the stick here, full transfer or equal sharing. Full transfer ionic, equal sharing is covalent. However, we have a lot of gray area here, or gradients, intermediate cases. Intermediate cases, of course, involve unequal sharing of electrons. So they don't completely transfer, but one gets pulled more than the other, two particular atoms between them. Okay, this results in a charge separation in the bond. So you have a partial positive, partial negative, just like the water. We talked about being polar. The oxygen, more electronegative, pulls it closer to there. And the oxygen side of the water would be partially negative. The hydrogen side would be partially positive. Okay, so here we're looking at examples of the types of bonds in our nice little diagrams here. You see these pictures show electron density for the most part. So chlorine here, Cl2, you see the electron cloud is like equal around both nuclei, whereas HCl, if you're looking here, you see that you have your tiny little hydrogen because it's really small. You have your much larger chlorine atom, but they form a covalent bond, chlorine being much more electronegative. The electrons spend more time and are attracted to the chlorine, and so you get this partial negative. This is a lowercase delta, you know, the Greek alphabet. When you have that little symbol in front of the charge, it means it's a partial charge. And over here, partial positive for the hydrogen, okay? Last but not least, the ionic bond, as you see, they are not overlapping in their density of the cloud. They are completely separate because the electron transferred. So the chlorine gained the electron and became chloride, and you have the sodium ion over here. But their clouds don't really overlap, but they are attracted to one another because you have a +1 and a -1, and the electrostatic force of the opposite charges, or the Coulombic attraction from the opposite charges, is what holds them together there. And that's why you see that they don't really overlap in their clouds, okay? Because they are completely separate entities, full charged +1, full charged -1, and now they attract to each other because they have the opposite charges. So, yes, and this is NaCl. Alright, so unequal sharing, the HF example here, as you can see, hydrogen fluoride. This also shows you density here, and you see the blue side over here is going to be the side with less electron density around it, the red side over here, more electron density. Fluorine being the most electronegative element on the table, it's going to pull. So if you're writing symbols, for the formula here, like the H would get the partial positive as indicated right here, the F gets the partial negative. Now, this arrow thing over here is what we call a dipole moment. And the dipole moment always points towards the more electronegative element, or the side that's going to be partially negative. And then the tail end of the little arrow kind of looks like a plus sign. So that's going to be on the side for the one particular side of the molecule that is partially positive. And if you have a directional dipole moment, that means you have two ends that are separate charges. One is partially positive, one is partially negative. Now you have a dipole. But if you have directional dipoles canceling each other out, then that's a problem, and that becomes nonpolar because you do not have a particular side of the molecule that is partially positive or negative because they all cancel each other out. We're going to look at an example like that as well. So, for example, because this is going to lead up to our little exercise coming up, the effect of an electric field on hydrogen fluoride molecules, okay? So here, no electric field is being applied, so you can see they're kind of just facing all different directions, kind of hanging out. Hydrogen fluoride would be a gas, so they could equally spread around the entire container, filling it completely. Now, if you apply the field, though, see that negative electrode right here, the partial positives attract to that particular one, so that's why all the hydrogen sides are facing that direction over there. Okay, and then over here is going to be the positive plate, so the negative sides of the hydrogen fluoride, which is going to be all the fluorides, they're going to point towards the positive plate, and they line up in the electric field like that. And this is also how those intermolecular forces get established, because this is a permanent dipole. So the positive ends of the hydrogen fluoride attract the negative ends of the hydrogen fluoride of a different molecule, and then you end up, it seals that attractive forces. And actually, since this is hydrogen fluoride, not only does it have LDFs, dipole-dipole, it also has the hydrogen bonding as its predominant force. So, now you're going to go ahead and draw some water, line it up in the electric field, and we will come back and take a look. Okay, so looking here, we should see, if you drew a couple of waters, the way that they should orient. The hydrogen sides over here, they should be pointing, okay, these are the partial positives, they should be pointing towards the negative plate. The oxygen side, the partial negatives, they should be facing and pointing towards the positive plate, okay? So they orient themselves that way. Once again, another good example here of has LDS, London, has dipole-dipole, and hydrogen bonding with the HO combination here. Now for the octet rule. The octet rule states that elements gain or lose electrons or share electrons to attain a configuration of the nearest noble gas. So nearest noble gas, for most atoms, and I qualify most atoms, that means they need 8 valence electrons. However, notable exceptions are at the top of the table, because the ones at the top of the table want to look like helium, and helium only has 2 valence electrons. So 2 valence electrons for hydrogen, lithium, beryllium, and boron. Obviously, they're a little bit, when we get into them, there are exceptions to some of the sharing rules, but they're not ones that follow the 8. They aren't going to be ones that follow the 8 rule. When you start with carbon, pretty much carbon down the table, they start following the octet rule. Like carbon will mimic and want the configuration of neon. So all of those elements, nitrogen, oxygen, fluorine, in that particular row, they're going to want to look like neon's configuration. And then, like you said, like sodium and magnesium, also they lose electrons to look like neon's configuration, and so forth. Okay? Electronegativity. The ability of an atom to attract a shared pair of electrons to itself. So basically, attracting electrons in a chemical bond is going to be electronegativity. Fluorine is the most electronegative element. Oxygen is the second highest here. Okay? So, very important here. Okay, the range of electronegativity values goes from 4.0, fluorine, the most electronegative, 2.7 for cesium. Like francium is also 0.7, but we kind of ignore francium because francium has a half-life of like 20 minutes and it doesn't last all that long. So most of the elements, the bottom rows of the table, you know, especially row 7 and the 2 that are below the table, a lot of those are radioactive. We don't really work with those elements all that often in AP Chem. Okay? Alright, so this basically is an electronegativity chart as like the one that's in the notes packet as well. Now you would never be asked or required to memorize the electronegativity values, but you should know that like fluorine is the highest, and then the bottom left corner is going to be the lowest based off of the trend. Noble gases, remember, do not count for electronegativity because they're not trying to attract electrons in a chemical bond. They are inert and unreactive entities, right? So here, I like this too. As you can see, it is a general trend. There are a few like exceptions in the middle, but like I said, you wouldn't be expected to know that or memorize it. If they gave you a data set to evaluate, then you could talk about how, yes, gold's electronegativity seems to be higher than mercury's, and you could probably look at atomic structure in order to be able to explain that. Or maybe it has something to do with gold being an exception to the Aufbau principle in the way that they arrange their electrons and so forth. Okay? But you wouldn't be expected to like know these values off the top of your head. And in the learning target, it said qualitatively, so we're doing it based off of the trend. So you basically just go with the idea that it increases as you go up a group, increases as you go across a period. All right, Coulomb's law. You thought you were done with it? No, it keeps coming back. Coulomb's law, the closer oppositely charged particles are to one another, the stronger the force of attraction, of course. That is going to have to refer to the R squared on the bottom. That's kind of the distance factor. Now, the greater the charge of the oppositely charged particles, the stronger the force of attraction. And that has to do with the Q1 and the Q2, which is the magnitude of the charge. Okay? So, when we looked at this before, we were comparing the magnitude of charge of the nucleus to the electron in the outer energy shell, or outer principal energy level. Now we're going to be applying it to ionic compounds and ionic bonds. So you'll see this application following through here. All right, so comparison of electronegativities and Coulomb's law. As you can see here, looking at boron. Boron's electronegativity value is 2.0, right? So this one is 2.0. And carbon's is 2.5. I'm just writing it out here because it's kind of hard to see. Nitrogen is 3.0. Oxygen 3.5. And fluorine is 4.0. Chlorine is 3.5. No, 3.0. Sorry. Chlorine's 3.0, I think. All right. So that'll give us a little bit of data here to look at and compare. So as you can see, boron, carbon, nitrogen, oxygen, fluorine, this is like going across the period, okay? So as you can see, the electronegativities are increasing. And they have the same number of principal energy levels. Everybody has 2 principal energy levels in the second row. But what you notice as you go left to right, what's increasing? The proton number, which means the effective nuclear charge is increasing, and therefore you get a stronger attractive force. Now, that's looking across the period, but if you compare like fluorine with chlorine going down the group here, you notice here that chlorine has 3 principal energy levels rather than the 2 principal energy levels that fluorine has. So this third principal energy level, even though has 17 protons, right? Okay, compared to the 9. So it does have a higher effective nuclear charge, but as you can see, adding that third ring with the third principal energy level creates enough distance here to where it weakens it slightly. I mean, not too much, because 3.0, like that's the same as nitrogen. Okay, it's still a pretty high significant electronegativity, but adding in that third one with the proton ratio of the 17 protons, its effective nuclear charge, it is slightly weakened by that larger distance, okay? And therefore it drops just a little bit, okay? So explaining our electronegativity values, trying to give you the Bohr model representation so that that helps you hopefully. Increases across a period. Effective nuclear charge increases due to the addition of more protons, increasing attractive force of the nucleus, magnitude of charge. The numerator of Coulomb's law increases if you want to think about it in terms of Coulomb's law. And like I said, this is a lot review even from our periodic trends notes. Decreases down a group, adding more principal energy levels, increases the distance, adds more shielding, decreasing attractive force of the nucleus. So distance, of course, you can also say that's the denominator in Coulomb's law, and you can refer to Coulomb's law. But if you refer to Coulomb's law, make sure you write in the equation, okay? You refer to any equation, and you want to use it as a relationship, you must write in the equation. So make sure that you do that. All right, so concept check. If lithium and fluorine react, which has more attraction for an electron and Y, in a bond between fluorine and iodine, which has less attraction for an electron and Y. So go ahead and see what you can come up with there. All right, so let's take a look. Between lithium and fluorine, which has more attraction. Anyone?
Fluorine.
Fluorine. Fluorine has the higher electronegativity. Yes, okay. But how do we explain this? Why fluorine's electronegativity is higher? Why is it going to have more attraction?
More protons.
Lithium has 3 protons. Fluorine has 9. So more protons of the fluorine gives it a higher effective nuclear charge, which allows it to have more attractive force. Okay, fluorine is significant because it only has the 2 principal energy levels and the 9 protons. That's sort of like a really supercharged magnitude of charge to the short distance, giving it super attractive force. Hence the really high electronegativity value and being the most electronegative on the table. In a bond between fluorine and iodine, which has less attraction for an electron, iodine is going to, okay? Now if you're comparing iodine with our fluorine here, that's going down the group now. So really the comparison now between iodine and fluorine has to do with the more principal energy levels, the farther distance. The more shielding, so weakens the force of the attraction, and therefore the fluorine being smaller, only 2 principal energy levels, whereas iodine has 5. And then that's why you would say that iodine has a weaker force of attraction with the 5 principal energy levels, creating a much farther distance and a weaker force of attraction. Okay, so as you can see, this kind of reiterates what's going on for all of the trends. Cross a period, proton number, cite something about the effective nuclear charge, and then say something about the strength of the force of the attraction. Going down a group, talk about the number of principal energy levels, talk about the distance, talk about the strength or force of the attraction based off of that distance, okay? And you will get all your explanations correct. Whether you're talking about electronegativity in this particular example, or whether you're talking about atomic radius, or electron affinity, or ionization energy, any of them, across a period, it's always the same reason. Down a group, it's always the same reason. And that's what they want you to say. But be specific when you're talking and comparing the 2 elements. Like if it's across a period, talk about the number of protons in each. If you're going down a group, talk about the number of principal energy levels in each. So be really specific to the particular 2 elements that they want you to compare. Okay? All right, now looking at here at our relationship of electronegativity and then how it compares to the bond type. Okay? Bond type here, electronegativity difference. If there isn't much of an electronegativity difference, it's mostly covalent, or if it's 0, it is purely covalent, which we would call that also non-polar, okay? And then as you have a larger electronegativity difference, you get into the polar, the gray area, and then if you have a huge electronegativity difference, it becomes like a full transfer of the electron, and now you're in the ionic territory. So it's actually quite a gradient, okay? Pure covalent is actually the same thing as nonpolar. So make sure that you understand pure covalent is going to be a nonpolar. Pure covalent or nonpolar, it says less than 0.4, but really it should be less than or equal to 0.4. Most charts do that. So if it's between 0.5 and 1.8, I would go with that. So 0.4 is usually classified into the nonpolar arena. So less than, equal to or less than 0.4. Then I would change the polar covalent to 0.5, between 0.5 and 1.8. Now, of course, if the difference is 0.5, then it's just barely polar. But if the difference is 1.8, then it's extremely polar. And then, of course, above 1.8, they usually call that ionic. All right? So you might want to make those changes real quick in your notes. And this graphic kind of shows it along the way here. The equal sharing, you see the electron density, of course, equally between the 2 nuclei there. Unequal sharing, one side's the one on the left is pulling more, so it's the partial negative. The one on the right gets less electron density, so it's partially positive. And as you get closer to the 1.8, that difference gets greater and greater. So you get a bigger dipole as you get closer to the 1.8. Like I said, 0.5, it's just barely a dipole. And as it gets stronger, as it gets closer to the larger difference. And then, of course, electrons transferred here, like you can see that the clouds don't even look like they're sharing anymore because they're completely separate, because they became positive and negative fully charged particle, and now they are only attracted to each other because of the electrostatic force or the Coulombic attraction between the full charge particles. arrange the following bonds from most to least polar. And like A is a question, B is a question, C is a question, so do them separately. Okay, so let's talk about these. Now, in all likelihood, what you're going to see on a test or an AP exam is not the electronegativity chart. They're not going to give it to you. You're going to use your periodic table to qualitatively decide. So if I'm comparing N to F, okay, I'm comparing that one with O to F, O to F, okay, and then C to F, over here to F, right? Okay, so we have N to F, O to F. You're supposed to be looking at the relative placement on the periodic table, not actually calculating the electronegativity values. So the ones that are closer together are going to be what? More or less polar?
Less.
They should have they should be less polar because their difference is going to be less. So that's how I would look at it from the periodic table. Don't waste your time trying to calculate it because they're not going to really ever have you calculate it. They want you to do it this way. So in that particular case, then the most to least, of course, most, this would be the first one, okay? Then the second, and then the third, okay? So you could list them like this, C to F, greater than N to F, which is greater than O to F. Like so, or you might see it written like that in an actual problem, okay? So, same kind of deal here with B. Now we're looking for, here we have C to F, like so. We have N to O, and then we have SI to F over here, okay? So the most, which one would be the most in that case? The SI to F, yes, this would be the first, this would be the highest, so the most. Then comes what? C to F, and then of course, and O's right next to each other, so that's going to have the least electronegativity difference. Last but not least, looking at the last example, CL to CL is going to automatically be what? Zero, right? This one's going to be 0 in terms of its electronegativity difference, so that's easy. That's pure covalent, which is totally nonpolar, like the pure end there. Okay, so boron to the chlorine over here, and then we have the sulfur to the chlorine. So the greatest is going to be boron to the chloride, then the sulfur to the chloride, and then of course ClCl is going to be the least polar. Actually, it's not polar at all by any means. Okay. The greatest electronegativity difference between the atoms, the more polar the bond. So you're looking for like a greater distance in the periodic table from one another. Greater distance is going to be a higher difference. Okay? All right. Which of the following bonds would be the least polar yet still be considered polar covalent? Try that one and see what you can make of it real quick. Okay, so once again, following bonds be the least polar yet still be considered polar covalent. I mean, I can easily eliminate this one because this is going to be nonpolar or pure covalent because O to O is going to be electronegativity difference of 0. That's easy to see, okay? Is there anything else I can eliminate just by looking at it? Really? Not needing to look at my periodic table? MgO. Why can I eliminate MgO?
Far away.
Well, it's a metal and a non-metal, so that pretty much describes what type of bond. It's an ionic bond, so it shouldn't be in the polar gradient area, right? Okay. Then we just have our other ones to look at. We have Si to O. We have C to O. And we have N to O. Okay, out of those, which one seems to be the closest together, which means it'll have the least electronegativity difference? It's going to be N to O. Very good. No. Alrighty. So, to be considered polar, unequal sharing must still occur. Choose the mod with the least electronegativity difference, and that's going to be N to O. So, opposite here, which of the following would be the most polar without being considered ionic? And we already said this one's ionic, and we already said that this is non-polar here. So, we're still looking at the three combos. We had the carbon to oxygen, silicon to oxygen, and the nitrogen to oxygen. So the most polar out of those three are going to be, or is going to be, the silicon to the oxygen bond is correct. So yes, once again, same idea that we're looking for the largest electronegativity difference, which means they're farther away from each other on the periodic table. Alright, how do we know which side of a polar bond is partially positive and which side is partially negative? Label the partial charges. So, we briefly talked about which way the dipole moment would go, which way is it going to go? It's going to point towards the more electronegative element. And in that particular case, the more electronegative element should be having the electron density more around it. So what side would be the partial charge there? Out of these two, silicon and fluorine, which one's more electronegative? Fluorine. So fluorine, of course, is going to get the partial negative. The silicon would get the partial positive. Out of chlorine and phosphorus, though, which one gets the partial negative? Which one gets the partial positive? Fluorine is more electronegative, so it gets the partial negative. The phosphorus gets the partial positive. If you're looking at dipole moments, the arrow would point towards the one that is more electronegative. It's like an arrow with a little cross tail. Okay? That's how you would draw a dipole moment if you had to draw a dipole moment. So just once again, relatively look at your periodic table. The one that's farther up and to the right that isn't a noble gas, remember noble gases do not count, is the one that you're looking for there, okay? Dipole moment, property of a molecule whose charge distribution is represented by a center positive charge and a center negative charge. You use an arrow to represent a dipole moment. Point the arrow towards the negative charge center with the tail of the arrow indicating the positive charge center. Okay? So, this is showing you water. Alright? And the electron density picture, I guess, is not in the notes, but as you can see here, the oxygen side over here is going to be the more electronegative side. So the arrow points from the positive to the negative side, as shown in this particular diagram. So if I was drawing it, say, into the electron density, I would also draw it this way, like so. This is going to be the partial negative. This side would be the partial positive side. Okay? Like so. Now, this is why, well, part of the reason why water is a polar molecule. First of all, the H to O bonds, the electronegativity is great enough, so that puts it in the polar category, in the 0.5 to the 1.8 category, right? But the shape of it, because it is bent shaped, and you know, if you draw the Lewis dot structure, it has the two lone pairs over here, whatever. So the directional dipole, it goes in one direction, and you do have one side that's partially negative, one side that's partially positive. So it creates these partial charges on each side. But in comparison to, say, carbon dioxide, okay? Carbon dioxide, okay, if you drew the Lewis dot structure, if you remember, it has double bonds like that. And we're going to get into Lewis dot structures, don't worry about that. But what you should notice here is that we have two directional dipoles, one going towards each oxygen, like so. And I'll draw that on the ball and stick because they're kind of hard to see here on this particular one right here. C to O bonds, if you do the actual like subtraction, O is 3.5, subtracting C, which is 2.5, that's a difference of 1.0. So the C to O bond is definitely polar. But because they both point outwards from the carbon and both oxygens are equally pulling, neither side has a partial positive or partial negative. It's like they're both pulling equally, so it's like both trying to pull the electron density apart, so both of them really are negative negative over here. So we don't have a dipole. They cancel each other out, basically is what's happening here. They cancel each other out, and that's when we said last year in honors where we said, is it symmetrical? Well, it's because the symmetry creates the dipole moments canceling each other out. So this particular molecule overall is nonpolar. So that's why carbon dioxide is rendered nonpolar. It has polar bonds, but the shape of it, the linear shape of it, creates it so that the dipole moments cancel each other out because it's very symmetrical. But when you're talking AP terms, you don't want to say, oh, it's symmetrical. You would say the dipole moments cancel out. That's what you need to say there, okay? They want you to use the correct jargon there. So that's why this way, dipole moments cancel out, even though this is a polar bond between the C to O. But because the shape of it linear and the dipole moments cancel out, we end up with a nonpolar molecule overall. All right, so here are some other examples of dipole moments just to kind of give you an idea. If you're looking at chloromethane, where you have the 3 H's but the 1 chlorine, you do end up having a dipole moment that points towards the chlorine. So this is going to be partially negative. This side down here is partially positive. It's a tetrahedral shape, and like I said, we'll get into shapes later, but as you can see, you do have one end that's partially negative, one end that's partially positive. That's why this little symbol means dipole moment. It has a dipole moment of 1.87. So it does have a slightly polar side to it, where it's partially negative. But if you look at tetrachloromethane, or this is also called carbon tetrachloride, the dipole moments point towards all of the chlorines, like so. So basically, every chlorine is pulling, pulling, pulling. Are any of the sides actually going to be partially positive then? No, they're pretty much like all the negatives around. The dipole moment ends up being 0. So carbon tetrachloride, or tetrachloromethane, which is the organic name for it, ends up being non-polar. So this one's non-polar, whereas this one has a slight polar edge to it. Okay? And you can kind of see, like, because the one on the left, you have 3 H's and 1 chlorine, the ligands are not the same, the outside atoms are not the same. Therefore, what you see is it's not symmetrical. Therefore, you're going to have a directional dipole. Here are some other examples, as you can see, okay, showing you the ones that have directional dipoles versus ones that do not. Hydrogen chloride, obviously towards the chlorine, but this one, this is a flat triangle one. As you can see here, this is formaldehyde. It goes towards the oxygen. So this one is going to be net dipole. Over here, ammonia, net dipole, it points towards the nitrogen. This is the carbon tetrachloride again. This one has 3 chlorines and 1 H, so it goes down this time. All the F's are pulling equally. This is one of those bipyramidal shapes, and then all the F's are pulling equally. That's one of the octahedral shaped ones. We will go over those, like I said, the shapes later on, but as you can see, they're symmetrical. SF6 is symmetrical. PF5 is symmetrical because the dipole moments cancel out. Alright, one more quick thing and then we'll stop. The relationship between the ionic character of a covalent bond and the electronegativity difference of the bonded atoms here. What you should notice is over here, we have lots of electronegativity difference. What you notice about all of these, they're mostly going to be metal, non-metal. However, HF is very close. HF's electronegativity difference minus the 2.1 happens to be 1.9. 1.9 technically puts it in the ionic category, but nobody thinks of HF as actually being ionic. Because just because the difference is 1.9 doesn't mean it has all of the characteristics of what an ionic bond is going to be able to do. So, basically, why isn't the bond of HF classified as an ionic bond? Because it doesn't meet the actual operational definition of an ionic compound. Any compound that conducts an electrical current when melted can be classified as ionic. So it has to be able to do that. The HF isn't able to conduct electricity. So the best way to classify bonds is really based off of the properties of the different compounds. And we're going to do a lab where we look at the different properties of the compounds to determine bond type.